Alright guys, so this is going to be part 1 of our review. We're going to be doing a tank problem. Well, we're actually going to be doing 2 tank problems. Let's start with the same one and then we're going to modify it just slightly. And so let's start with a tank that has the same flow going in as it's going out. Let's say it's 10 gallons per minute and going out 10 gallons per minute. So I just did G, but that could be grams, right? Gallons. And let's say that the concentration is going to be of 1, is that a lot? Maybe 0.1. Maybe too little. Okay, now too little. 1 was okay, 1 pound of salt per gallon, but now I put 0.1, so whatever. 0.1 pounds per gallon of some salt. Maybe it's a very dangerous salt, so it has to be a low concentration. And so here we will have to find out the concentration going out. So let's say that we also have an initial volume in this tank of, let's say, 100 gallons or 500 gallons. Why not? We're making numbers up, so why not? Go big. And let's say that initially we have about, so this concentration will be 0.1 pounds per gallon. So let's say that we start with a higher concentration. So we have 500 gallons. 0.1 would give me a 50. And so let's say that we start with 100 pounds. Wait, 500? Yeah. So let's say that I start with 100 pounds of salt. So now let's go ahead and try to solve this and figure out what will be the concentration, or what will be the amount of salt in the tank at time t. I'm going to call that S of t. It's going to be amount of salt as a function of t in the tank, so as a function of the time. And that's going to be given in pounds. And so then we're going to talk about time given in minutes, because my units there say minutes, time in minutes. And I'm saying that the initial amount of salt from my diagram, it says that there's 100 pounds. All right, so let's see what happens here. So the change of the amount of salt with respect to time is given by the flow in of salt. We don't care about the water and everything, just the salt minus flow out. And ideally, if we do everything correctly, the units for this would be, and that's very useful to check that you're doing things correctly, it should be given in pounds per minute. That's what we call the time. All right, so let's see how that works out. So the flow in, we have 0.1 pound per gallon, but there's 10 gallons flowing in per minute. And we see how gallon cancels gallon, and we need to have pound of salt per minute. And then minus, here I need the flow out. So now there are S pounds of salt in the tank, but I'm not getting all the 100 coming out. They're diluted in 500 gallons of liquid. So this is pound per gallon. I need something that is gallon per minute, so I can cancel gallon and get like pound per minute. What do you see here? There's gallon per minute. Well, that flow there. So actually, I'm going to put the 10 over there. Hit this star. And that gives me my differential equation with the initial condition that S at 0 will be 100. All right, so let's write it just as let's just first eliminate all the constants and all the units and all that and deal with it as it should be, at least in my opinion, which is just like that. And then my initial condition that S at time 0 is 100. So this is technically a linear equation. You can add and do your integrating factor, but it's not needed. It's actually a bad idea to do it that way because this is also separable. Now, the next problem, we will change one of these two, and that's going to give us a different situation. So we're going to have to do dt. At that point, you do have certain dt. At that point, you will have a linear equation that you will actually have to solve by finding the integrating factor. So I want to divide by 1 minus, actually, you know what? Let me multiply everything times 50. So I'll write it as 50, and I distribute it here, so there is 50 over 50. Why did I do that? Minus s. The only reason why I'm doing that is so my u substitution is relatively simple, but I made a mess in the process, so was it worth it? I don't think so, but, you know. But the reason why I want to do that is because whenever I integrate, I do the u substitution. U equals 50 minus s, and then the u is negative ds. And so my 50 already came out here. So it's kind of nice. I mean, at least I think so. So I get negative 50 integral of du over u. And then this is just t plus c. My marker is starting to get really faded. Let me go get another one. Bad news, guys. This is the last one we have, so we'll have to order. So natural log of the absolute value of u is going to be equal to negative 1/50th of t. I mean, technically the negative 1/50 that affects the c, but since I haven't chosen my c based on the initial condition, I can just rename it c with impunity. So that works out. Then I exponentiate on both sides to obtain that u is going to be equal to another constant, e to negative t over 50. So here I'm going to go ahead and I'm going to substitute this in, and I'm going to rewrite the equation as it should appear. So I'm going to do a little bit of algebra. Please, if you don't agree, just pause the video, do the algebra yourself, plugging the 50 minus s in here and solving for it. And so you're going to end up with that s is 50 minus c e to negative t over 50. The reason why I did it accelerate like that is just because I want to do the initial condition, and I have just this little space. So using that initial condition, that s at 0, what is s at 0? This is one that you got to be very, very careful, because in Calc 2 you were used to just plugging 0 and getting 0 back for everything. But here it's not the case, because you get an e to the 0, which is 1, so minus c. That one survives. And that's going to be equal to, what do you say, 100. So then c turns out to be negative 50, actually. And so this becomes a plus 50, and I can rewrite my equation, and we'll discuss it. All right, so this exponential, what it's telling us is that, well, the important bit here, I suppose, is that the limit as t goes to infinity. So what's going to happen as this system achieves a steady state? So as t goes to infinity, this term goes to 0, and I go back to 50. So when we take the limit as t goes to infinity of this quantity, we get 50, which is, I have my concentration of 0.1 pounds per gallon times 50 gallons. That would be 50 pounds in the tank. So we start with 100. We're putting something that is less concentrated, and as it starts flowing out, eventually we get steady state where this concentration becomes the dominating concentration, or the concentration of the entire tank. All right, so I'm going to do one now where I change the flow. So I'm going to make an 20 gallon going out instead of 10. And we'll see how that changes everything. All right, so for part 2 of this video, we're going to consider the case when the tank is actually emptying out. So we're getting more volume out than we're getting in. The variables I'm going to keep the same, so I'm using this same equation, same idea, a mass balance here of salt. So before we had already said that the amount of salt going in was going to be 1 pound per minute, multiplying 0.1 times 10. So this was going to be given in pound per minute. So this was all right. And now this is the one we have to pay a little bit of attention, but not too crazy. So here I'm subtracting, and I have 50 what? Why did I say 50? S is what I wanted. S there. Pounds of salt in the tank divided by the volume. That's going to give me pound per gallon. And I have 20 gallons per minute. So I'm going to have gallon per minute, pound per gallon, give me pound per minute. So that is the unit that I need. However, the volume now is not 500 because the volume is changing. So for every minute that goes by, I'm really running out of ink. I hope that you can still see it. If not, I'll have to do some magic there with the computer. Hopefully you can still see. Pop the color even if I disappear. I have another marker, but I don't know if it's any better. Let's try it. Oops. The cap didn't quite work. Bloopers galore. So the volume is going to be given by 500. That's where we start. But for every minute that goes by, the volume of the tank is dropping by 10 gallons because you have 10 gallons going in, 20 going out, 10 minus 20 is 10, negative 10, sorry. And so you're getting minus 10 times T. For every minute you lose 10 gallons. So that is what we're going to plug in here. So my differential equation becomes ds dt given by 1 minus S, or 20S rather, over 500 minus 10t. Now, this one is a linear equation, no matter what you do. So you're gonna write it in that form, S prime plus, and here this is all, they all have a common multiple, 10. So maybe we're gonna write it as 2 over 50 minus t, S equals 1. So that's the form of it. I think this one is even more invisible because it's finer. So I'll go ahead and get back to the one that I had. So this is now in this form. I need an integrating factor, which is going to be of the form e to the integral of 2 over 50 minus t dt. And this is going to give me a u substitution of the form u equals 50 minus t, du is negative dt, and this becomes e to the 2, or negative 2, natural log of 50 minus t. Ugh, this is becoming invisible. I don't have to write in orange if there's going to be any hope of us seeing this. So I'll continue writing in orange. I apologize that it's going to look a little bit ugly, but it is what it is. So this negative 2, I have to put it as a square, and it becomes e to the natural log of 50 minus t to the power of negative 2. Now, e to the negative log cancels, and then I have to multiply times just this, because they're inverse functions to one another. So I multiply times this on both sides of the equation, and on the left-hand side, I'm going to get 50 minus t to the negative 2s, the whole thing prime, that's the whole point of the integrating factor, is going to be equal to, and I multiply times this quantity, which I'm going to write as 1 over, why? I can't integrate it like that. I don't know, I'm fighting with myself at this point. Minus t squared. So I can integrate both sides of the equation to get 50 minus t to negative 2s. And here I have to integrate doing a u substitution. U equals 50 minus t. Du is negative dt. And then I have u to negative 2. Add 1 to exponent is going to be u to negative 1 times negative 1. But I had a negative 1 in front, so this is just going to give me 1 over 50 minus t plus c. And then I multiply both sides of the equation times this. And I get 50 minus t plus c times or over 50 minus t squared, but I'm write as 50 minus t to the negative 2. And at this point, I have to use my initial condition that at this point right there, okay, I did save it. So I'm going to erase that and I'm going to substitute in with my initial condition and we will finish this problem. All right, be right back. All right, so as I said, we use our initial condition that said that S, that was not the right marker, that said that S at times 0 is going to be equal to 100. So let's plug that into here. So I get that S at times 0 is going to be equal to 50 plus C over 50 squared is going to be equal to 100. So this is going to give me 50 when I subtract, and then C is going to be equal to 50 cubed. Okay, great. And so I want to have that S as a function of time is going to be equal to 50 minus t plus c over, C, I already have it, 50 cubed. But look at the magic. Over 50 minus t squared. Magic is that. Is that 5 theta? 50. That this function is only valid until this thing empties. And when does that empty? Well, that empties when my volume, which was the 50 minus t, no, the volume, I calculated it. It was 500 minus 10t. So when t is equal to 50, that function equals to 0. So this is only valid from 0 to 50 for the values of t. That's why I cannot really talk about limit as t goes to infinity, because, well, this term would go out to infinity. And then you can see that if I plug in here, well, I cannot even plug t equals to 50 included, because at that point the concentration would go out to infinity, because you have that the volume went down to 0. So since concentration is amount of salt divided by volume, then this term would blow up to infinity. So it's something that you have to be mindful of, and that when you solve these kinds of problems, when the volumes are different, either the volume eventually will, or the tank eventually overflows, or it goes completely empty. When it overflows, it's not that big of a deal. We have a plus, because since you assume t to be positive, at least you don't have the zeros in the denominator. But in this particular case, because we're assuming that the flow is negative, or the net flow is negative, then we're getting these to empty out. And then the volume becomes 0. Anyways, but that's at least how you solve this problem. So we'll wrap it up here. We'll leave it at that. And thank you for watching, and I'll see you in the next one.